All right, so in this video, we're going to be combining everything that we've learned so far. We're going to be adding our 1D kinematics and our vectors lessons together.
I was smiling?
Roll the intro.
Do you feel the vibes?
All right, so if we're going to start extrapolating this into multiple dimensions, we'll have to recognize that there will be an X direction, a Y direction, and possibly a Z direction, although this one we mostly ignore. In the X direction, we'll have its own velocity Vx and Vy, and this can be our initial velocity Vx naught and Vy naught. So these represent our initial velocities. We then can have an acceleration in the X and an acceleration in the Y. This does not change our kinematic equations. We will still get the same three basic kinematic equations: x final equals x naught plus v naught t plus 1/2 at squared. Then v final equals v initial plus at. And finally, Vf squared equals V naught squared plus 2a delta x. The only main difference here is that we'll have two sets of them. So we'll also have a y final equals y initial plus V naught yt plus 1/2 ay t squared. We can fix all of these to be V naught x, ax, V final x, V initial x, ax, and so on, right? So then we'll get v final y equals v initial y plus ay t, and v final y equals v initial y, both of those squared, plus 2 ay delta y. And keep in mind the y's are subscripts that are only there to denote what direction the thing is going. Right? So when we looked at our vector analysis, we could break things up into components. So if we have all of our component along the x direction, that would be this group here. So this is all of our x direction stuff. And likewise, we can have all of our y direction stuff be separate. If we can use the information separately, great. If not, we can recombine it or take it apart into its component form at any individual time. So let's say I have something like a V initial is equal to 10 meters per second at 30 degrees above the horizontal. Well, what that means is I'll have to use SOHCAHTOA to break this apart into its v naught x and v naught y. So if I break it up into v x naught and v naught y, let's just make this v naught x. The subscripts are completely and totally interchangeable, so you could say v naught x or vx naught. I might switch between them every once in a while, just based on whatever I feel like. They're all just bookkeeping things, so they're not really that important other than so that you can remember what they're for. So if I look at SOHCAHTOA, the opposite that I have is V naught y. So I can get that the sine of 30 degrees is equal to, well, V naught y over the hypotenuse, which in this case is V naught. So V naught y over 10 is equal to that, the sine of 30. So now I know that the sine of 30 times 10 is equal to V naught y. Likewise, I can see that the cosine of 30 degrees is equal to V naught x over V naught, which would be V naught x divided by 10. Ergo, 10 cosine 30 is equal to V naught x. So this is how I can break things apart and put them into their individual components to find these variables that we need. Now, sometimes you may have to use similar triangles. And this is another one of those things from trigonometry that can get kind of annoying. So if we scroll down a little bit, I'll show you an example of where that comes up. So if I have a person who has aimed, let's say a Nerf gun, at something in a tree, because their friend is hiding up in the tree and they want to hit their friend in the tree with their Nerf gun. Well, let's say their friend is 10 meters away and 10 meters up is a very tiny friend. So now that means that if the person has aimed the Nerf gun and shot at that angle, V0 will have the same angle as this distance angle here, right? So this hypotenuse for our distance will be at the same relation to our V0. So this angle would be, in this case, 45 degrees. And that means that our initial velocity would also be at 45 degrees, simply because these are similar triangles. So the basic theory behind this is to just split things up into their individual directions, x and y, and treat them as separate quantities. Now, we do have one slight problem with that, which is that if we treat them like separate quantities and we're asking for something that happens when something else happens, we won't be able to solve. We'll have two equations with many unknowns, and that would be bad. So the only thing that we can use that goes between the x and y directions is time, t. So oftentimes what we will be doing is solving one direction for time and plugging that into the other direction to solve for the thing that we're looking for. So let's say in our example where we have our 45 degree velocity and our 10 meters and 10 meters at the tiny friend, we would want the time at which the projectile reaches this spot, right? And we would know that at that time, it will have some specific height associated with it when it is at a distance of 10 meters. So we would use the x direction and put in 10 meters, solve that for time, and then plug that time into the y direction, and that would equal our height. So this process is how we can solve any of our motion problems in multiple dimensions. We just solve one dimension for one thing and plug it into the other dimension. That thing is usually time. Also keep in mind that our V0 goes between these two dimensions because it is in both dimensions. So while V0 sine of 45 will equal V0 y, and V0 cosine of 45 will equal V0 x, this V0 and this V0 are the same thing. So I could also say that V0 is equal to V0 y divided by the sine of 45, if let's say I know how fast it's going upward. And then I could use that to find V0 x, let's say. So then I would put in V0 y over sine 45 cosine 45 is equal to V0 x. So you could easily do that, or if you have some way to solve for the initial velocity, you might be able to figure out the angle, or you might be able to figure out some other things. And then you could cross that between both dimensions. So now this all gets relatively complicated if we have accelerations in both the x and y directions. That's because both of those are quadratic equations for x and y in time. And so we'd have to use the quadratic formula in one and then plug it into the other, and it gets a little hairy. So in order to simplify it, we'll be looking instead at something called projectile motion. That's going to cover about 99% of the two-dimensional kinematic problems you're going to deal with. So in the essence of making this video not super long, we're going to cover projectile motion in our next video. So make sure that you like, comment, and subscribe, and check out the